Hello physics students, this is Dr. Brenzy. This is lesson 5.2.1, and our objective for this lesson is that we're going to be able to define something called angular acceleration and use it to describe the motion of a child on a merry-go-round. It's been a while since we've talked about circular motion, so I want to review a couple of important concepts before we dig into angular acceleration. So the first thing I want to talk about is angular displacement, and that is basically this angle theta that you see here. So let's say that I started at point A and that at some later point I went to point B. Well, if I did that, then my angular displacement would be theta. Okay, so theta is the angular displacement, and it is measured in any unit that you use to measure angles. Oops. So it can be measured in degrees, it can be measured in rotations or revolutions, or it can be measured in radians. Radians is the one that we like to use in physics the most because there are some formulas that we use where you have to use radians. So just to remind you how to calculate radians, so theta in radians equals your distance on the circle, the circumference of the circle particularly, divided by the circle's radius. So if this is a length of s meters, then I can say that theta in radians equals this distance s that I traveled along the circle divided by the circle's radius r. So if I happen to travel a distance of r along the circle, then I have traveled, let me put that as radians, I have traveled 1 radian. And by the way, I should make this look like a table instead of 2 fractions there. If I have gone a quarter of the circle, well, it turns out that a quarter, well, actually, let me back that up. Let me do a whole circle. So if I do a whole circle, we know that that is a distance of 2 pi r because that's the circumference of a circle. And if I do that, then theta is going to be that divided by the radius, which turns out to be 2 pi. So when you go around a full circle, you've gone 2 pi radians. A half circle, you have gone half that distance, which is pi radians, or half that angle. And I'll let you figure out what a quarter circle would be. And if you predicted that that's going to be pi over 2, you would be correct. Okay. So these angles are pretty important ones to remember. Alright, so that's angular displacement. So angular speed, if you remember, we used the letter omega. It's a Greek letter to define angular speed. And that is the rate at which angle changes over time. Oops. Let's do some spelling here. So if I change my angular displacement or my angular position by some value delta theta, which means change in theta, and I do that over some time, delta t, then the result that I get when I take those, when I divide those two, is my angular speed, omega. So if, let's draw a little table here. Just to kind of give us an idea of, so if I happen, let's say that I go a distance of r along my circle, so my delta theta would be 1 radian, and let's say it takes me 2 seconds to do that. That means my delta t would equal 2. So if it takes me 2 seconds to get from this point to this point, that means that my delta theta is equal to r divided by r, which is 1, which is why I put delta theta as 1, my change in angular displacement. And if I did that over 2 seconds, my value of omega would be 1 over 2, which is 1/2. And the units would be radians per second. This is in seconds, of course, and this is in radians. Well, let's say that over the next 2 seconds, I went another radian, so after 4 seconds total, I go 2 radians. Well, 2 divided by 4 is the same as 1 over 2, so I have not changed my angular speed. It's still 1 over 2 radians per second. Now let's say that I go a little bit faster, so instead of covering 1 radian 2 seconds, let's say I cover 5 radians in 2 seconds, then omega would be 5 divided by 2, which is equal to 2.5 radians per second. Okay. So now we're caught up on angular displacement and angular speed. It turns out that there are a couple of equations that you can write when angular speed is constant. Now, if you go way back to Unit 1, when we were talking about linear motion, motion in one dimension, we know that when the speed is constant, you can write that speed equals the change in distance over the change in time. Well, it turns out that when you're talking about angular motion or rotational motion, I'll put rotational, because we're talking about motion around a circle. Okay. It turns out that we have a very similar formula. Omega equals the change in theta over the change in time. Now let's take a quick look at these two equations. We're talking about, in both cases, about displacement divided by time. In this case, we're talking about linear displacement, displacement along a line over time. and that gives us our linear speed. When we talk about rotation or motion around a circle, we have a change in angle or angular displacement divided by change in time, and that gives us our angular speed. So if you can remember that these equations, or this equation over here, and you can remember that linear speed is the same as rotational speed on a circle, then you can remember this equation over here. Okay. Now we got to be very careful here, because on a circle, let me draw a circle here. On a circle here, before we went on break, we talked about both angular speed, omega, that's our change in angle over time, and we also talked about linear speed along the circle. Okay. Now, when I'm talking about this omega and this v, I'm not talking about this omega and this v. I know that sounds confusing, because if we're talking about motion on a circle, I'm talking about, we would say, omega times r equals this linear velocity on the circle. That's not the same as this velocity right here. What I'm saying over here is that if you think about motion along a line, and you have some sort of velocity v, that you can write a similar equation for this velocity as you could for this angular acceleration. Okay, so when I'm talking about this equation and this equation, I don't want you to think about this v right here, the tangential velocity or the tangential speed. I want you to think about motion along a straight line and motion around a circle. Okay. Now, just like we have acceleration along a straight line path, we can also have angular acceleration. So imagine that you're on a bicycle and you're at rest, and let's say that for some reason this bicycle wheel is free to spin as quickly as it, well, no, actually we can still describe. We can put you on the road. So we'll put you on a street, and you're at rest, so the angular speed of this wheel is 0 when it's at rest. But as you start pedaling, this wheel starts to rotate faster and faster. In other words, its angular displacement divided by time is getting faster and faster. Well, just like you would say that linear speed gets faster and faster due to acceleration, you could say that angular speed gets faster and faster due to angular acceleration. In physics, we use the Greek letter alpha to represent angular acceleration. And we measure this in radians per second squared, or radians per second every second. Sometimes you can measure it in degrees per second squared. Okay. But usually we prefer to use radians, because sometimes there are formulas that only work when your angle is measured in radians. So just like you would say that acceleration along the line is equal to the change in velocity over the change in time, you can also say that alpha is equal to the change in angular speed over the change in time. So as this wheel is spinning faster and faster, that means we would have a positive angular acceleration. And as it is slowing down, getting slower and slower, you could see that this angular acceleration is getting closer and closer to zero. Now, here's another example of what angular acceleration would look like. There's a link I have both here and in the comment section if you're watching this directly from YouTube. It's a quick video, 15 seconds, and I want you to click on it and watch. And what you'll see is you're going to see a child, or two children actually. They're going to start a merry-go-round going around from rest. And as the children run around the circle to get the merry-go-round going faster and faster, there is an angular acceleration alpha. Then, when the children hop on the merry-go-round and they let it coast, you'll notice that the angular acceleration is zero because angular speed is constant. So, when the angular speed is constant, alpha equals 0. When angular speed is changing, then this angular acceleration does not equal 0. Okay, well, there are some equations that we can write when acceleration is constant. We can write, just like if you think back to Unit 1, we can write displacement along a line equals d sub I plus omega I times t plus 1/2 a t squared. You can also write for angular acceleration, you can write theta equals theta I plus, oh, I put an omega in there, didn't I? That omega doesn't belong there. That should be a v. I'm already getting them mixed up. Omega I times t plus 1/2 alpha times t squared. And we have a second equation that you can write when acceleration is constant. You can say that the velocity is equal to initial velocity plus a times t, and you can write omega is equal to initial omega plus alpha times t. So there are really no new equations you have to memorize. You just have to memorize these equations and then remember that you change d to theta, you change v to omega, and you change a to alpha. Linear distance, angular distance or angular displacement, velocity, angular velocity, acceleration, and angular acceleration. Okay, so that is what I wanted to go through this today, and I look forward to showing you some examples in class, and talk to you soon. Bye.